performance regressions. So this talk is kind of meant as kind of statistics crash course for software engineers. As such, I would like to apologize to guys who are better mathematically grounded. I will be taking some shortcuts, simplifications, and occasionally do some inaccurate expressions in an effort to somewhat simplify things, so that it's actually usable for ordinary software engineer. So the daily bread and butter of our team is that basically you have two kernels or two versions of distribution or whatever, two versions of glibc, and you want to see whether the performance didn't regress or whether you even improved and whatnot. And the performance is measured by a set of benchmarks. We have them automated in tests. That's a package that like people in SUSE probably know. Our team is continuously running like 15 machines which are running benchmarks, plus we have a couple of other machines which can be used to like investigate the individual regressions that are then detected. Now this is not what I'll be talking about today. It's just to provide some setting. Each benchmark essentially outputs just some number. Yeah? It will not be important for us today what this number means. Or it can be also several numbers which somehow characterize the performance. And now what we do is basically, we want to figure out from these numbers whether the performance improved or not. Yeah. So the kind of naive approach is, just take the number, compare them, and you have the result. Yeah. Why to complicate things? So let's try to let's give an example here. So for example, you have here somehow dbench completion times. With 6.4 kernel and 6.8 kernel, you got like 32 with your try on 6.4 kernel and 36 with like 6.8 kernel. Yeah. Now, if you try, so it seems from this that 6.8 kernel is just slower. Yeah. So wait a minute. If you try again, then you will get numbers like, for example, here, like these are actually measured numbers, 23 and 27. Yeah? So now you may be getting suspicious, but still 6.8 seems slower. Yeah? But if you do a few more tries, then you get numbers like 27 versus 21. So now 6.8 suddenly looks faster. 26 versus 25. So again, 6.8 is somewhat faster. Yeah? So which one is actually better when you have numbers like this? Yeah? That's the question we have here. Now, probably all of you have heard about things as average. Yeah? So when you are in a situation like this, that it's kind of going up and down, then you do several measurements, you take the average, and then compare averages instead. Yeah, that's like secondary school level kind of math, or even basic school maybe. So here for the sample here, you get like averages like 27 and 27.25. Yeah, so the 6.8 again looks slightly slower. But if you do repeat the same procedure again, you do you again get like 4 measurements from each kernel and compute the averages. Then you get like 26.5 for 6.4 and 23.75 for 6.8 kernel. Yeah. So again, like in the first set of measurements, 6.4 kernel was slightly faster. In the second set of measurements, 6.4 kernel was significantly slower, or significantly by about 10%. Yeah. Whether that is significant or not is yet to be decided. So what you do in this situation, you have like average in one case is better, in the other case it's worse. So now it's time to kind of take a step back, think a bit about what's happening here, so that you can actually decide properly which kernel is actually better, or whether they are actually the same, or what's happening here. So this is the situation we are frequently faced with in performance team, that you measure the performance, the numbers are going up and down, and now you want to figure out actually whether something changed or not, whether it's just normal. And so there is natural variability in the performance numbers you measure due to many different factors. Yeah, like there can be some background processes running in the system, like cron jobs getting scheduled. Yeah, or NTP date running. We actually had to turn that off in our performance measurements because occasional NTP date decided to update the current time. It was confusing some of the benchmarks. There are also other differences, like more fundamental, like differences in cache content or in the code alignment of the binary as was loaded into memory, differences in CPU scheduling or NUMA node placement, which affects timings, or differences in CPU frequency scaling. So basically the CPU itself these days decides on which frequency it's going to run. Yeah, you can somehow influence it from the operating system, but you usually do not dictate it exactly. It's in the CPU, this decision. And based on the decisions, of course, if the CPU decides to lower its frequency because it thinks it doesn't have enough work to do, then everything runs just slower, which affects obviously your performance numbers. Similarly with ACPI sleep states, if the CPU decides to idle, then it then takes some time to wake up from this idle state, which again influences your performance numbers. So overall, the contemporary computers are rather chaotic systems, actually. There is a lot of stuff happening. You don't have control about a lot of it. And small change, in the initial conditions actually has relatively large impact on the outcoming or on resulting performance numbers. So what can we do with this variability? And there are two approaches what you can do with this variability. One is to try to control this variability and get rid of it in your measurements. And the other is to use some statistical methods to differentiate between the noise and the signal in your measured data. Now, basically, what are you going to do pretty much depends on what you want to measure. Yeah. So this talk will be mostly about the second thing, but I will touch briefly on the first thing as well. And for non-trivial benchmarking comparisons, which you do, you will probably need to employ a combination of both of these approaches. So first, let me touch a bit on the attempt to control the variability, which is kind of the first approach which people tend to take. So if you gather some benchmarking data, you see, there is a noise, which is big enough that, it's making the comparison hard. Then you try to reduce the noise to kind of get the decision. Yeah. So the sensible steps to do are to, remove this background work, like the cron jobs and TP, but also there are various background, for example, file system cleanup tasks, yeah, or other like tasks getting scheduled, for example, by the kernel, which are not so easy to get rid of. You can also bind the tasks to CPUs or to bind memory to NUMA nodes, and similar stuff to kind of reduce the influence of the CPU scheduling decisions, reduce the timing differences due to access latencies to the remote memory on other NUMA node or so on. You can also force the CPU to high frequencies using the performance CPU frequency governor. Yeah, you can disable ACPI sleep states to reduce the latency of these transitions and so on. This all can be done. But then, the question is what you really are interested to measure, yeah? Because are you still measuring after you do all these special tunings, are you still measuring, what you are interested in? If you and the answer can be both yes and no, depending on what you are actually looking for. If you do some simple code change and you want to some optimization of some algorithm inside the kernel or in your application, whatever, and you want to measure whether it improved performance or not, then maybe all these tunings are perfectly fine because you are really looking whether your code particular special code is more efficient or not. And these are all indeed uninteresting like perturbations to your measurements. And then, doing all these fine tunings is perfectly fine. On the other hand, if you do kind of more, let's say, macroscopic benchmarking, where you try to more approach the production conditions the real customers are going to see, then you cannot really afford to do all these tunings because the customers aren't going to bind the tasks to the CPU nodes. They aren't going to select the performance governor because they want the power savings. They don't want to pay the power bills of the server running constantly at maximum frequency. So then these tunings are in fact unrealistic, and you simply have to live with the fact that there is a variability introduced by, for example, CPU frequency scaling decisions. And then when you have this inevitable variability, then come the statistical methods. So, you now have to live with the variability, and the question is how to live with it, how to decide, given the variable data, whether actually, the performance changed or not. And here I will be speaking a bit about, I will introduce a bit of terminology here, but it's really the bare minimum of some statistical terminology so that we know what we are speaking about. So from the statistics point of view, the measurements, say, of time we do on one kernel are considered to be samples that are, drawn or taken from some unknown distribution. Yeah? So these are the numbers. The numbers we measure are considered to be some random numbers where you have certain probability you get this number, certain probability you get that number. The example of like how, let's say, the distribution can look like is here in the bottom in the graph. So there you see like what's the probability of getting each particular number. In computers, this distribution is actually continuous. So, it can give you arbitrary real number. In practice, we really get more like a discrete distribution in computers, but in principle it's the same. Yeah, basically it assigns the possible probability for each value you can get. Yeah. And then this distribution can be characterized by certain parameters. Probably everybody know what is a mean. Yeah, that's kind of the average value you are expecting to get. There are other parameters like median or 95th percentile you can be interested in, and like relatively often are interested when doing performance comparisons. So median means that's the value where if you take a random sample, then you have exactly 50% probability that the value is smaller, and then the median, and 50% probability that the value is larger than the median. Yeah? So right in the middle. So in this case, actually, the mean and median are different because the distribution has, comparably higher probability of relatively large values. So this skews the mean more towards the right. And 95th percentile is kind of similar to median, but with 95%. Yeah, so 95th percentile means that 95% of like expected values are below this value of the 95th percentile. And this is interesting, for example, when you want to somehow make sure that there are no extra big latencies, yeah, then you constrain the 95th or even 99th percentile, whatever. And so, we have these samples which are drawn for one kernel. We have samples which are drawn for the other kernel, yeah, from some random distribution. And basically, we are interested whether the means of the distribution usually are different or not. Yeah, that shows whether the kernel, that means whether the kernel kind of regressed or not. And now, because you don't know the actual distributions, yeah, you can only measure the samples from this distribution, but you never have all the samples. Yeah, you can always do more. So your estimate of the mean is never exact. Yeah. So you measure some samples, you take the average of these samples, and this is your estimate of the mean. But if you do it again, you will get a slightly different estimate of the mean. Yeah, and the statistics captures this by so-called confidence intervals. So basically, what statistics tell you is not that the original mean of the distribution is this, but you can learn information like that with 95% probability. The mean of the distribution for the kernel lies in this interval, yeah? Some average minus delta, average plus delta. And for the other kernel, with 95% probability, the mean lies in another interval. And maybe to demonstrate this on the example, here is it computed for our D-bench numbers. So, we have here these 4 experiments with D-bench, and they are plotted in the graph on the right. The red rectangles are the average values that we have computed there, and the bars denote the confidence intervals we have computed for the averages. Yeah. You can basically, there are standard statistical methods how, given the measurements, you can compute the confidence interval. I will not go into the formulas now. If you are interested, you can find them very easily on the internet. But if you look at the confidence intervals, it's now clear that basically, you cannot really statistically differentiate between the two kernels. The confidence intervals, 95% confidence intervals are overlapping. So basically, you don't know whether one kernel is better or not. Okay, so let's continue. And now we have kind of done this. So here we have looked. That the confidence intervals are overlapping. So we don't know, but how to capture this in some automated way? Yeah, how to do this? Like how to get some algorithm which will decide which will compute the intervals and decide about this. And there is a standard method for this, and that's so-called t-test. Yeah, I will be speaking here about Welsh t-test. There are different flavors. Again, not that important for our task. And it's the standard statistical approach. How to use this, notion of distribution means and confidence intervals to decide whether the two sets of samples, here they are denoted by x1, that's the sample from the x1 are samples from the first kernel, x2 are samples from the second kernel, and we want to decide whether the average, whether the mean has slightly shifted or not. So on up there you can see the formula for this decision. That's the Welsh t-test. So you basically take the difference of the averages divided by some formula, whatever it is. Yeah, you can there see the definition of the variance of the test sample. That's the formula in the bottom, or to be more precise, it's actually called unbiased estimator of sample variance, in statistical terms, but you can forget it right now. Just call it variance. And based on this, there is some constant nu there, which actually, you have to determine, and this constant depends on the confidence with which you want to do the decision. Yeah. So, but let's say you decide for 95% confidence, so then you can look up in the tables what's the proper value of nu for your 95% confidence. Plus, it also depends on the number of samples you are gathering and so on. But that number nu can be simply determined, and you will do this comparison of this expression, and it basically is a way how to decide exactly whether the confidence intervals are going to overlap or not. Yeah, and if this inequality holds, then with your desired confidence, you can tell, yes, the x1 is average of x1 is actually or the distribution from which x of the first kernel has larger average than the distribution of the second kernel. So basically your measured quantity has decreased between the two kernels. Okay, now, so can we always use t-test? Because, not many, the t-test is kind of standard recommended, let's say, statistical tool. But if we actually used it in our performance measurements, we have found out rather frequently that the results the t-test gives us are not actually matching reality. And so we were kind of investigating why. T-test has the assumption that the averages are normally distributed. So it doesn't have to be that, let's say, you measure the time to complete as we did with dbench. So you do not need that the time to complete are normally distributed, but for the t-test to be valid, you need to know that if you compute the average of each sample you take, then that the averages will follow the normal distribution. Normal distribution is this shape over here. Everybody probably knows this. It's otherwise called also bell curve or Gaussian distribution, Gaussian curve. It's this nicely symmetrical distribution that's well concentrated around the average value. Yeah. And so, can we really assume that the averages are actually normally distributed? On one hand, it doesn't take that much for them to be normally distributed. And this fact is captured by so-called central limit theorem. And, what central limit theorem says is kind of captured in this image here. So basically, you are taking random samples from arbitrary distribution. The distribution can be like very weird, like that one drawn over there. It doesn't really depend in any way on the distribution. You are taking samples from this distribution, and the central limit theorem says that if you take enough samples and you take their averages, then the distribution of the averages is going to follow the normal distribution with some parameters. Yeah. So independent of the distribution, if you take of the original distribution, if you take enough sample, then their averages should be following the normal distribution. So this seems to imply that, like, whenever you take enough samples, then the t-test would apply. Yeah. But when we actually apply this in reality, as I said, it actually didn't work like that. That's when the theory kind of meets the reality. So for example, here you have like average throughput numbers as output by FIO, doing random writes to some hard drive. Yeah. And this is the histogram of the throughput numbers we were getting. Yeah. And it doesn't look quite like a normal distribution. It's kind of bit shifted to the left, and kind of the tail here is kind of heavy. Yeah. Actually, if you compare it with the normal distribution, so the red columns are now samples drawn from a normal distribution, like the same number of samples, the same mean and standard deviation, and the random samples looked like this. So you can see that they are really more concentrated. If you really use the normal distribution, that they are more concentrated in the center, and the tails are not so heavy here. And actually, I should have taken more samples, but for it to be better visible, but I didn't have really enough numbers collected. So why isn't the throughput? Why aren't the throughput numbers following the central limit theorem? Yeah, it is mathematics, so somehow you would expect it that if you have proven something, that it should hold. Yeah, and if the reality shows that it doesn't hold, then some of the assumptions of your theorem must be broken. So what is it? Why doesn't it work? So the averages we have taken here, like the average throughput numbers, are actually taken over 25 seconds worth of write-back, which means it's a couple thousands IOs that are happening there. So it should be kind of enough to, for the central limit theorem to apply. We have like 150 throughput numbers gathered here. So that should be sample already kind of large enough to show the normality. It would be better to have like 500 or 1,000 samples to show better that actually the distribution of the throughput really is not normal. This could be still that we were just really unlucky with the throughputs. But yeah, if you would do more, then you would see that still really the distribution is not normal. And the problem actually, so what is broken here is the assumption of the central limit theorem on the independence. Yeah? So if you recall, then basically you were taking these samples from the original distribution, and the central limit theorem states that we have to take them independently. So you take one sample and then you take second sample, and the value of the second sample should not in any way depend on the value of the first sample. Yeah? And then you take third sample, and this should not in any way depend on the first two you have drawn. And this is actually assumption which is not really true in computer systems. Yeah? Because if you do one measurement, then the result of the second measurement you do very much depends on the value of the first one. There is a lot of system state that's carried over from the system, from the moment you do the first measurement to the moment you do the second measurement. Yeah? So there is the state of system caches carried over, the state of the scheduler heuristics, yeah, what has happened in the past on the system is carried over. The CPU state is carried over. Yeah? The CPU has internal, let's say, branch prediction heuristics and other stuff that's carried over between the two measurements. The placement of your task in memory is again carried over. Yeah? So there is a lot of system state that's actually carried over between these two, between the two measurements, and this causes the two samples you measure not to be actually independent in this like probability or statistical sense. Moreover, this carryover of a state is actually fundamental for good performance of computers. Like the reason why caching works is exactly because it carries over the state. It remembers that you have used this in the past, and it keeps it in a cache so that it's faster next time to use it. Yeah. So you don't want to get rid of this dependence because this is what's making computers fast, and you rather want to measure how good you are at this carrying over of the state. But that's make it basically impossible to really get statistically independent samples. So, okay, so it's kind of difficult situation. So the question is how you can then sensibly measure the performance if you don't get independent samples. The central limit theorem doesn't apply, which means t-test cannot be really reliably used. So how to do the performance comparison then? So first thing is gather good data. Yeah, so this means enough samples, but also like do several benchmarking runs. So for example, you run the benchmark, it gets you, I don't know, 100 measurements. Yeah. But then you run the benchmark again and you get another 100 measurements. This is important because if you execute the benchmark for the second time, a lot of the state is actually lost from the first task. So the samples you are gathering from the second benchmarking run are more independent, at least to one another, than if you collect them in a single process. Yeah, you can even do reboots between runs or recreation of the file system between runs and so on. And this even further reduces the amount of state that's carried over between the measurements. And so you get lower dependency between the samples you gather. And so it improves, let's say, it improves the, let's say, estimate of the confidence you can have in the results. Yeah. So gather enough samples, run the benchmark several times, like run the benchmarking binary several times, and ideally reboot between the runs. And then once you have gathered the data like this, then you still like have some amount of dependence in your data, because the numbers, usually it's not feasible to do, let's say, measure one number, then restart everything, measure a second number, restart everything, and do this 1,000 times. Yeah, that will kind of take a lot of time, and it's infeasible to do this. So usually you have to do something like measure 100 numbers, restart application, measure 100 numbers, restart application. Yeah, then do the reboot. Yeah, then do this couple of times. This is still kind of feasible. But then you have some amount of dependence in your data, so you still cannot strictly use t-test, and you have to use some more advanced statistical method which can deal with at least some amount of dependence in your measured data. And for this, there is a statistical method called bootstrapping. There are actually several more methods which can be used, but bootstrapping is the one which we use inside tests to deal with this. And so bootstrapping is kind of the method that you are given some n samples, yeah, x1 to xn, and there is some amount of dependency, but we assume that we have gathered enough samples to somehow characterize reasonably good enough the original distribution. Yeah. And you want to estimate the mean and the confidence interval of the mean, essentially, of the original distribution. And so the bootstrapping method is the following algorithm. So out of these n samples you get, you randomly with replacement select some m samples. M can be in principle smaller than n, but in the simplest case you take m equals n. So you draw with replacement as many times as you have the original samples. So here we will drawing 5 times. So first we will select number 26, then we randomly select number 19, then we again randomly select 26 again, and that's fine. This means with replacement. Yeah. So the numbers can in principle repeat. We don't care. Then we select 18 and 25. Yeah, so this is our new vector which we have selected from the original samples, and we compute average from this sample. Yeah, so this average of this actually method of random selection is called resampling, and the average of the resampled numbers is this one. Now, the trick of the bootstrapping is actually to do this a lot of times. So repeat this like 1,000 times or 10,000 times, actually, that are about the repetition counts that are suggested in the statistics literature. So you select another vector with resampling. So now you select 23, 18, 25, 23, 18, for example. And the average will be 21.4. And you do this, say, 1,000 times. Yeah. So you get like 1,000 averages for these selected samples. And then there is something which is called like bootstrap theorem, and that says that if you do this enough times, then the distribution of these averages you have computed is going to follow very well the distribution of the original samples you have drawn from the first distribution. So in particular, you can use the variance of these averages as a good estimate for the confidence interval of your average. Yeah? So this is like the statement of the bootstrap theorem. Anyway, in practice, what this means that if we have these 1,000 averages and we take a median, let's say, of these averages or of these mean values, then this is actually a very good approximation of the true mean of the original distribution, and we get also some good estimates on the confidence interval of our average. So this is then And this is then how we use the bootstrapping method inside tests to really deal with the sample variance. So at least for some of the benchmarks where we gather enough samples and so on. So, we get the results from some k benchmarking run. Yeah, each benchmarking run gathers some n samples. Yeah. So altogether we have like k times n samples. Now for each benchmarking run, we use the bootstrapping method, like which I have just described, to compute some means, expected means of each of the benchmarking runs, and some variances like sigma squared of each of the benchmarking run. And then the average of the averages is actually the final estimate of our value, the measured quantity. Let's say the time to complete is the expected time to complete is actually the final mu value here. And then from the variance of the averages and also of the variances inside each individual run, we will compute with this formula. And I do not plan to explain this. You can take it as a nice image. But this is actually what's used to estimate the confidence interval of the original value. Yeah. And there is, it's not that difficult, but I guess to derive this formula, it's kind of, intuitively it says that the confidence interval depends on how much inside each benchmarking run the numbers vary, and as well on how much of variance we get between individual benchmarking runs. Yeah. So with this formula, we estimate the confidence interval of our computed value. And this method is robust in presence of some dependence in the measured samples. Phew. So, this was the method. Now, that's basically all I had to cover today. So basically, if I should somehow summarize it about the recommendation for the benchmarking, if you have to do it. Yeah? So take enough samples and arrange for some sample independence if possible by restarting the benchmark several times, rebooting between several runs and so on. And also reduce the unwanted variance you can get rid of when you have in mind like what you are looking for. So in some cases you can reduce the variability a lot by constraining system a lot. Sometimes you cannot, depending on what's your use case, but it's always good to get rid of a variability you are not interested in. And then either use t-test if you have good reason to believe that your numbers are independent. So if you see that the noise isn't kind of big, or you do not really expect there to be a big dependence between your obtained sample, then you can just apply t-test, which is simpler. If you cannot really be sure, then you should be applying this bootstrapping to reduce the influence of dependent values, and you get the value and the confidence interval out of this more advanced method. And then when you are comparing the two kernels, you have to you can really say that the two kernels are different, or two systems are different if the confidence intervals don't overlap. Yeah. So if they overlap, you cannot really tell. It's statistically not possible to decide with given confidence whether the kernels are different or not. But if the confidence intervals don't overlap, then you can tell, yes, with 95% confidence or so, the kernels are really different, and this one is better than the other one. And that's all I had today. So thank you for attention. So if there are any questions, we have like 5 minutes.
Okay, so what about bimodal distributions? Means essentially if your program has a fast path and a slow path and a common path that is taken by both, and you have an improvement in the common thing, but you have a regression in the slow path, then the improvement in the fast path may mask the regression in the slow path, but you still might be interested in the slow path. So is there a trick to that?
So yes, then basically, it can happen that the mean will just, say there is no statistically meaningful difference between the means. Yeah, that's what this method is able to say to you. If you want, if you actually suspect that there is something like this happening, then you need to be estimating other parameter than the mean. Yeah. You have to be estimating a parameter like median, for example, or you have to be estimating some percentile, and which, like, this method applies as well to other parameters. It doesn't have to be applied to the mean. It as well applies to all the same distribution parameters like median, percentiles, and so on. Bootstrapping can be used as well. Like, we don't have it implemented in MMTest, but in principle, the method applies. So then you have to select other distribution parameter which would capture this property, and that depends. Actually, you have to know what you are looking for to be able to design the method to detect it.
Yeah, which means you should probably get some understanding of the distribution before choosing which parameter.
Yes.
Okay. Yeah. Thank you.
Yeah.
So on the subject of variability and dependence of the data or the samples, the results you see, how much do you consider external factors for your test system? Because you talked about memory system, CPU, frequency scaling, things like this. But I'm more thinking temperature, or if you're using a large JBOD of HDD's temperature in there as well as noise. If your fan starts kicking in, the noise pressure from the fans on the HDD will affect the HDD performance. So you will have dependence on external factors as well. So I was wondering if that's parameters that you're also considering in your.
Well, so this is kind of the source of the noise in your benchmarking data, yeah? And we also observe like interesting external factors in our benchmarking results. So ideally, you should gather enough samples in different enough conditions that this will be captured as the noise both in the baseline data and the test data. So then this will appear as kind of increased size of your confidence intervals, and that's it. Then you can statistically decide whether it's still like meaningful difference or not. But in reality, you get the baseline data on Monday, yet test data on Friday, and your server on Monday doesn't have to necessarily be the same as on Friday. We have seen that, like, somebody decided to reconfigure the BIOS in between, yeah, or some DIM went bad in between, and that skewed the benchmarking data. We have seen that as well. So then you investigate and you see, okay, the data is garbage and I have to start again. Yeah. And there is like no generic solution for this, because if the systems is just different, like, again, you can modify your test procedure to gather some data for baseline, some data for test, then again for baseline, again for test, do it in interleaf fashion like this to reduce influence of this like system reconfiguration. But it's never going to be perfect, and you have to figure out what's practical for you as well. So there is probably no great answer.
So, hi, quickly and rather on more on the technical side. You said that this is implemented in MMTest.
Yeah.
And I knew about t-test, but that's true even for bootstrapping.
Yes.
Even the rebooting between.
So rebooting between benchmark is not really implemented.
Okay.
Or well, that's not part of MMTests. You can.
Marvin, well.
Yeah, it would have to be in Marvin, and Marvin doesn't support it yet. So
but it's going to be. It's
yes.
Yeah. Cool.
Yeah. Okay, I guess we have run out of time. So if someone has questions, please catch me afterwards. I'm still here until tomorrow. So thanks for attention, and see you later.